Hello dear students, so welcome back to our class. So today we will continue with our group theory. So there are some standard results which we will prove, and we will also see some more examples of groups. Okay, so one result that we have is the uniqueness of the identity element of a group. Okay, so we may write this as a theorem. Theorem in a group there is only one identity element. Only one identity element. Okay, so there cannot be two different identity elements. Okay, so this is an important theorem, or it can be stated this way: so that identity element in a group is unique. Okay, so that way also you can show. So this is basically uniqueness of identity. Okay, this is the thing. Uniqueness of identity. So how do I prove it? Okay, the proof is very simple. Let G be a group, and suppose that G has two identity elements. Okay, has two identity elements. Okay, say E and say E bar. Okay, suppose these are two identity elements of a group G. Okay, so let us take the composition also. Say G star be a group. Suppose that G has two identity elements, E and E bar. So what I have to prove is E and E bar will be actually equal. Okay, so suppose you come up with one identity element E, your friend comes up with another identity element E bar. Okay, then I can always show that E and E bar are actually equal. Okay, right. So how we can justify it? Using the properties of the group. Remember, there are only four properties. One property is you take any two element A star B, A and B, so A star B is always in G. Okay, then you have the associative property A star B star C, this is equal to A star B then star C. Okay, this is there. Another one is the existence of identity. There is an element E which satisfies this. A star E equal to A equal to E star A for all A. Okay, inside G, right? And another one is existence of inverse. Given any A inside G, there exists B inside G, is that A star B equal to identity equal to B star A. Okay, so these are the properties which a group satisfies. Okay, so let us try to prove that using these properties of identity or the properties of group, how we can show that E and E star are, E bar are actually equal. Okay, so since E is identity and E bar, this is an element inside G, right? We have supposed that G has two identity elements, so this E and E bar, they are all elements of G. Okay, so by property of identity, what will happen? You see this property of identity element composed with any other element gives the element itself. Okay, so here E is the identity element, so E bar or E star E bar, this will be same as what? The element itself. Means consider E as identity, so E star E bar will be same as E bar only. Okay, and again, since, so you can denote this as 1, and since E bar is identity, okay, the next step I consider E bar as identity. Okay, and E belongs to G. Okay, E bar is identity and E is an element of G, so what will happen? E star E bar, by that definition this is also equal to E, because here I have considered E bar as identity. Okay, so there are two parts here. One is A star E equal to A, and there is E star A equal to A. Okay, means whatever way you compose, it is going to be the same element there, right? So here is just I have used one part, E star E bar. This is equal to E bar because E is the identity. E is an identity. I can't say the till now because I have not proved. So E bar is identity and E belongs to G. So E star E bar will be equal to E because E bar is your identity element. Okay, so here the first part is applicable. Here in the first one, the second one is applicable. Okay, right? So from 1 and 2, what do you see? Oh, sorry. What did I do? E bar is identity and E belongs to G. E is identity and E bar belongs to G. So E star E bar will be equal to E bar, right? And yeah, so yes, it's okay, E star E bar. So from 1 and 2, what do you see? You see, compare the left hand side. Left hand side is E star E bar. Here also in the second one, left hand side is E star E bar. So from 1 and 2, we can see that E bar and E, they are equal because the left hand side is equal, right? Okay. So from 1 and 2, we see that E bar is same as E. Okay, thus a group has only one identity element. Okay, has only one identity element. Okay, so this is proved. Okay, so very simple, just 1 or 2 marks problem, right? Okay, let us come to another problem, that a group has a unique inverse also. Okay, means for each element the inverse is unique. Okay, so that is called the uniqueness of inverse, right? So let us do it. This is also a theorem. For each element A in a group G, there is unique means only one. Okay, only one element. So in the definition we did not say unique. Okay, in the definition we said that given any A, there exists an element, okay, in G which satisfies A star B equal to E. So for each element A in a group G, there is a unique element B such that A star B equal to E equal to B star A. Okay, where E is what? E is the identity element. E belongs to G is, so now we will start writing the identity element because we have shown that it's unique. Okay, identity element. Okay, so in another other way, we can also state it this way: in a group, every element has a unique inverse. Okay, has a unique inverse. Okay, and this is another way of stating the same theorem. Okay, so if in exam it's the statement is this, then don't get confused. This to mean the same thing. Okay, that is why I have written both the things here. Okay, so how do I prove it? Let's see. So in the proof, let us start with an element or the set G. Let G star be a group. Okay, let G star be a group, and let us take A belongs to G. Be any element. Okay, be any element means we are starting with an arbitrary element of G. Okay, that is why this line is important. Be any element. Okay, Also let E belongs to G be the identity, okay, be the identity element. Okay, suppose E belongs to G is the identity element. Identity element, right? So by definition of group, by definition of group, so definition of group says that for this element A there is an element, there exists an element B inside G such that A star B equal to identity equal to B star A. Okay, right? By definition of group there is such element B. Okay. Now what I do is I have to show that there is only one such element. Okay, so we will suppose that, let us suppose that there is another such element, somebody finds another such element. In that case what will happen? Okay, suppose there exists C in B G such that A star C equal to E equal to C star A. Okay, we suppose that by definition we get at least one element B in G, okay, which satisfies this. Next we are supposing that, okay, let us suppose that another element C is there in G which satisfies the same thing. Okay, so what is our motive or what is our aim? We have to show that B is exactly equal to C. Okay, so here to show, or say we claim, means we are confident enough that if somebody comes up with two different B and C which satisfy the same thing here, then we can always be confident to show that we claim B is exactly equal to C. Okay, this is what we claim. So how we can claim it? Just using the properties of group. Okay, so we have A star B equal to identity, right? So what we do is we compose both side with this C. Okay, so let us compose this C star A star B. This will be equal to C star. Okay, this is always true. We compose. So when you compose in groups, remember that either you have to compose in the left, means you have to apply the operation in the left, or you have to apply the operation in the right, because it may happen that A star B is not equal to B star A. Okay, there are groups which do not satisfy this. Okay, so that is why one is pre-compose. This is called pre-composition. This is actually called pre-composing. Okay, pre-composing C. And another is post-composing. Post-composing is if you write it the other way, A star B star C, okay, equal to E star C. That is the post-composing. Okay, so here we are pre-composing. And then what property I can apply here? By the property of group, I can apply the associative property. So this will be C star A star B. This will be equal to, what is C star C? C star E. E is the identity element, so C star E will be just C, right? So here also you can write the reason, since C star E equal to C. Okay, since E is the identity element, it's better to write it this way, since E is identity element. Okay, is identity. Okay, now what is C star A? By our supposition here, what is C star A? C star A is nothing but the identity. Okay, so here we replace C star A by identity, so it's E star B equal to C. So E star B is again B, so B is equal to C. Okay, right? So here itself, from here itself, we can show that identity inverse of each element is unique. So thus every element in G has a unique inverse. Okay, so there is only one element which satisfy this. Okay, so since we have done the uniqueness, we will adopt one notation for inverse. Okay, so since inverse of each element in a group is unique. Okay, so there is only one element, so we denote the inverse. Okay, the inverse of A in G as A inverse. Okay, so we introduce this notation A inverse. Okay, so many a times we will use this particular notation A inverse for the inverse of an element in G. Okay, usually. So if your addition operation is addition, many times we will see that this inverse is actually denoted by minus A. Okay, if if the operation is addition, okay, we often denote it as, then we denote inverse of A as minus A. Okay, we will see for the group this integers we denote it by minus A. Okay, and for other groups or say arbitrary groups, it's usually denoted as A inverse. Okay, so all this is possible because this identity and inverse elements of any group are unique. Okay, so let us take another theorem which is very familiar to all of us. We have been using it since our childhood. Okay, so if you have something like say twice x equal to twice y, what we do immediately in the next line, we cancel 2 and write x equal to y. Okay, so this is the cancellation law. Okay, so we will see that in a group, if we define a group, immediately the cancellation law actually holds. Okay, so it makes the things simpler, right? So let us try to see. So this is actually called the cancellation law. Left cancellation law, right cancellation law. Okay, so left and right cancellation laws. Cancellation laws. Okay, so these things hold in a group, right? So the proof is very simple, just by using this. Proof is this. Let I did not state the theorem itself. Okay. So in a group, G, comma, the left and right cancellation hold. Okay, the left and right cancellation law, cancellation laws hold. Okay, hold means they are satisfied. Okay, that is for A, B, C belongs to, or A, B belongs to G. Sorry, A, B and C. That is for A, B, C belongs to G. Say A star B equal to A star C always implies B equal to C. Okay, this particular law holds. Means if we have A star B equal to A star C, immediately in the next step we can write B equal to C. Okay, means A can be cancelled from the left side. Okay, and from the right side also this is true. B star A equal to C star A. This will always imply that B equal to C. Okay, so this is the left cancellation law, and this is the right cancellation law. Okay, we are cancelling from the right side. Okay, right. So let us try to prove it. Okay, not that difficult, simple. So proof proof is this. So let G star be a group, and A comma B comma C belongs to G. Okay, so these are some elements, right? Okay. Okay, so let A star B equal to A star C. Okay, suppose this is true. So this will imply what? So we have for the element A in G, okay, we have A inverse is also in G. Okay, so this implies A inverse star A star B, okay, is equal to, or let us do it independently, means just by the definition. Okay, so in some books the cancellation law is given earlier than uniqueness of inverse. Okay, so let us do it independently just by definition of group. Okay, so let us just write, since A belongs to G, so there exists an element say A dash or A bar, such that A star A bar equal to identity equal to A bar star A. Okay, so we have not denoted still written about the identity, so let us write where, what is this E? E is the identity element. Okay, identity element in G. Okay, thus A star B equal to A star C implies that, so we compose A bar on both sides, so it's A bar star A star B, this will be equal to A bar star A star C. Okay, and then we use the associative property, so it is A bar star A star with B, this is equal to A bar star A then with star C. So this is what, this is the, so while writing in exam also please try to mention the reasons. This is associative property. Okay, and here we will apply this result. Okay, A bar star A is E, so E star B equal to E star C, so this will imply B equal to C. Okay, that is the thing. So the left cancellation law is proved. Okay, similarly we can prove the right cancellation law. Okay, similarly, so if in exam you are asked to prove only left cancellation law, then you can stop up to whatever we have done, and if you are asked only right cancellation law, then do this part, and if you are asked both, then do both parts. Okay, similarly, let we have say if it is something like B star A equal to B star C star A, this will imply B star A then star with, so here we are taking post multiplication or post composition. Okay, so this is pre multiplication, then post multiplication. Okay, so we usually say multiplication also, so this is post multiplying. So even though the operation may not be multiplication, okay, so post multiplication. Post multiplication by what? A bar. Okay, so this will imply B star, again I apply the associative property. Okay, so B star A star C, this will be same as C star A star A. Okay, so this is the associative property, right? This is the associative property. So from here we can again write, this is B star E equal to C star E, so this is B equal to C. Okay, so thus the cancellation law holds. The left and write cancellation laws hold. Okay, write cancellation laws hold. Okay, so these are the results. So 3 theorems we have done: uniqueness of identity, cancellation law, uniqueness of inverse. Okay, so some more problems we can, we had I had given you some problems, so meanwhile you try to discuss. In the next lecture we will do some more examples, then subgroups, okay, other properties of groups, right?